Welcome back, everyone, to the eCoreAcademy e-learning platform. My name is AJay, and I'm back here with another Algebra 1 video for you all. Thank you all for tuning in. This is our transformation of linear functions lesson. We're going to be taking a look at the basic translations and transformations of a linear function, and we're going to see how exactly they affect their graphs. So I'll explain to you what the different types of transformations are, the translations, and then the vertical compressions and horizontal compressions and stretches. And then, of course, I'll explain that in depth with our actual unit. So just to recap with our unit, how this whole Algebra 1 unit is structured, we're on to our very fourth unit of this Algebra 1 Algebra 1 course. Tanya will be teaching the odd numbered units, and I'll be teaching the even numbered units. So we've bridged into our fourth unit, and our first lesson in this unit was evaluating function basics. Now we're going to be taking that function, our linear functions, and we're going to be adding different twists and turns to their transformations and seeing how we can affect the graph and what are the properties of a graph. So before we jump into the lesson, please make sure to do 4 things. Please make sure to smash that subscribe button, hit that like button on this video, turn on post notifications, and feel free to comment down below. We appreciate all of your feedback. So without further ado, let's jump right into it. Let's take a brief overview of what exactly transformations are. Some of you might be confused, but if you think about the word root of transformations and what exactly they are in terms of linear functions, it's fairly simple. So we're going to talk about the basis of the linear function in this video. So the whole point of this video is to take a linear function and actually alter it in some way by adding something to the function. So the slope-intercept form is a linear equation that we're going to be focused on. We're not going to use standard form or point-slope form in this lesson. Slope-intercept form helps us see transformations the best. So all linear functions will be written in slope-intercept form of y equals mx plus b, something that you've already learned at our Algebra 1 course here. And just to recap, remember that m is actually your slope in the equation that determines how steep or how much of a slant and how steep the line is, your linear function. And then b is your y-intercept, where exactly your equation is crossing the y-axis in relation to the coordinates of x and y. So you can plug in your x and y points, create a table, and graph it. And what are transformations now? Transformations are merely factors altered or added from the original equation, the original linear equation. We can change any of the existing variables within the equation, or we can start adding different factors to the equations in terms of a specific variable we like to call k. And I'll explain what that is as well. So once we add these factors to the original equation, we're going to change its positioning and its appearance on the actual graph itself. We'll still keep it aligned, but we'll start to change some of its properties. And I'll explain exactly what those are and how those rules are categorized. Now, some of these basic transformations include your stretches and compressions. These are your horizontal stretches and compressions and your vertical stretches and compressions. So how exactly is the graph being stretched out or compressed towards either one of the axes? And then, of course, we have our translations. These are more basic when we're going to be doing that for the first half of this lesson. It's about shifting, basically moving the graph itself to the right, left, up, or down. So these are your horizontal and vertical translations. I'll be showing you how to actually add the numbers, what variables are added to an equation, and how they actually look on a graph. So let's start off by looking at vertical translations. And the vertical translation, how to think of it easily, you're basically just changing the y-intercept to increase or decrease the y coordinates all throughout the given, your given graph to either make it go up, move the graph up 1 unit or a couple units, or down a couple units. So a vertical translation is when you increase or decrease the value of the y-intercept, and by doing so, you're increasing or decreasing all of the y values. Think about it, because when you have your equation f of x equals mx plus b, that b value is going to be added to your slope multiplied by your x coordinate. So it's always going to be added to the equation to either increase or decrease your y value, which is your f of x. So it'll increase and decrease it, and when you do so, when you increase or decrease that y-intercept, you're going to be either shifting the graph up 1 unit, just on the vertically, you're going to be shifting it vertically up, or you're going to be shifting it vertically down, depending on what you're adding as k. So k is that variable that we're going to be adding. That's your vertical translation variable here. So when you add k to this equation, you're actually just going to be altering it, shifting it up or down. So let's take a look at our parent function. This is our original function, f of x equals 2x plus 2. We call it the parent function because it's the original function that we're actually going to transform. We're going to add things to it to actually change it and see how it compares to the original graph. So on the left-hand side, let's take a look at a specific scenario where we'll add k in this case, where k is -3. So we're going to take f of x equals 2x plus 2, and like I said, that k value there, I underline -3 because that's our k value. We're going to be minusing 3 as well on top of it. And in this case, since k is less than 0, we call this a vertical shift downwards. Because k is less than 0, it's going in a negative manner. That means you're going to be subtracting 3 from all of your y values, meaning it's going to move downwards. Your whole graph is just going to shift downwards 3 units specifically. And then on the right-hand side, I'll show you an opposite situation. You're going to have f of x equals 2x plus 2, but in this case, we're going to substitute k for +1. And in this case, since k is greater than 0, I apologize, that should say greater than. Since k is greater than 0 in this case, 1 is greater than 0, it's a positive number. Any positive numbers in this case, it'll move your graph up in this case. So this will be a vertical shift upwards, and by the given unit, it's going to shift up 1 unit. Now let's take a look at what these vertical translations look like on a graph. So the visual translations. We'll take our original parent function, 2x plus 2, and we'll graph those first. So on the left-hand side, we have our equation 2x plus 2 minus 3 is for k is less than 0. So we're going to graph our equation here. This is our original equation of 2x plus 2 here. Now what we're going to do is, since we're subtracting 3 units, we're actually going to shift this straight down 3 units. We're going to shift it down 3 units on this graph. So we're going to go straight down 3 units, and that's going to be your new translated graph. This graph is going to be the graph of 2x minus 1, because right here we see this k value here. You can subtract that from 2. We know that our y-intercept has now changed to -1. Therefore, our graph here is at -1 here for our y-intercept, and it's just shifted down 3 units. On the right-hand side, going in the opposite way, this is supposed to be greater than. I apologize. So f of x equals 2x plus 2. We're going to be adding 1 to this graph, so that's going to move it up 1 unit. So we'll graph our original equation, f of x equals 2x plus 2. Then we'll add that 1 to the equation. This makes our y-intercept now 2x plus 3. So that means we're going to be moving up 1 more unit. So we're going to be moving up, and we're going to graph that unit. So both of these graphs, as you can look in both of these examples, the lines themselves, they haven't changed. They don't add any curves or anything. It's still one line. But you're just merely changing the positioning of this line. The slope stays the same. The only thing that's being changed in this vertical translation is the y-intercept. Now let's take a look at horizontal translations. And this has to do with changing the x-coordinate instead of the y-coordinate. So a horizontal translation occurs when you increase or decrease the value of the x-intercept or the x-coordinate. Like I said before, the y-intercept was changed in the last one as a result of you adding k to the whole equation. But in this case, when we add k only to the x-coordinate, we're going to be changing the x-intercept. So we're going to be changing the x-intercept in this case. And when you change the x-intercept is when when the graph, whenever it comes to intercept, like your y-intercept is when the graph intersects the y-axis, but in this case, the x-intercept is where the graph intercepts the x-axis, so the x-intercept. When the x-intercept is changed by a horizontal translation, it'll increase or decrease all of the x values, which causes the graph to shift left or right. So instead of moving up or down vertically, horizontal translation, when you add it properly to the x value, you're going to be moving left or right, horizontally. And then as you can see here for the translation, we're still going to utilize the same translation factor of k, but in this case, k is only going to be added to your x value. So from our original equation, we have f of x equals mx plus b, but in this case, it's just going to be m times x plus k, then plus b. So it's going to be m times that x plus k originally. So k, x, and k are going to be added together, and not for the entire equation. So as we can see here, this is our parent function here, 2x plus 2. We're going to keep it the same. And now we're going to alter it. So we're going to take our original equation, f of x equals 2x plus 2. Then we're going to change x. We're just going to add 1. We're going to add a positive 1 to x itself. So now it's 2 times x plus 1 plus 2. We're only changing the x coordinate. So now this is an example for x is greater than 0. So any values that are greater than 0, this would cause your horizontal shift to move leftwards. So this would shift the graph leftwards the amount of units, so leftwards 1. Now you might be thinking, wait, that doesn't make sense. Normally when I think of positive, you're moving on the right on a number line. However, it's actually the opposite only for transformations. When it comes to transformations and changing the horizontal axis, when you're changing it horizontally, it's always going to be the opposite. So when you're adding a value, you're going to be moving leftwards. And then on the right-hand side, we're going to use x minus 3 as our other example. And this is for any values that are less than 0. And when you're moving when you have a value that's less than 0 that's added to your x, it's going to be a horizontal shift to the right. So this time you're going to be adding 3. You're going to be moving to rightwards to 3. And then when you're adding 1, you're going to be moving leftwards 1. So let's take a look at the visual translations, what these look like on a graph. So f of x equals 2x plus 2, our parent function. We're going to graph 2 times x minus 3 plus 2 when x is less than 0. Sorry, k is less than 0. And in this case, we see that we have our original function, f of x equals 2x plus 2. We're going to be moving to the right 3 units. And then that's our new graph. That's our graph just merely being pushed 3 units to the right. That's all it is. And as you can see here, the slope is actually changed. The slope actually does not change in this equation. Actually, it stays the same, just like a vertical translation. However, you're just merely altering the x-intercept. And then, of course, here we have f of x equals 2x plus 2 being changed. Here, we're going to be adding a 1 to the x value. And when you add 1, remember, that's going in the opposite direction. So you're going to move left 1. And you're going to get your y-intercept at positive 4 because you changed your x-intercept as well. So as you can see here, the graphs change, moving rightwards and leftwards, your horizontal translations. Now let's move on to vertical stretches and compressions. This is where you're going to be changing the y-coordinate by a factor. So instead of adding things, we're actually going to be multiplying to change the y-coordinate. So a vertical stretch or compression occurs when the graph's y-axis causes the graph to compress towards the x-axis and become flatter, or stretch away and gain a larger slope. And the x-intercept always stays the same. So what exactly are we doing here? Let me dumb this down a little bit so that this makes a lot more sense. And then, of course, we can take this to a higher analytical phase. So when we're taking our original graph, say, for example, f of x equals 2x plus 2, we have our slope of 2. Remember that. So what does a vertical stretch and compression do? All a vertical stretch or compression does is it's basically just changing the slope. So it either makes it slanted, it either makes it more slanted, or it makes it flatter. So that's why I'm saying towards, or compresses towards or away from the x-axis. When it comes to a compression, that means that the graph will actually start to flatten out and get closer to the x-axis, start to hug towards the x-axis, being pushed towards there. And then, of course, when it comes to a vertical stretch, that means the graph is actually being stretched away from the axis. It becomes steeper. So flatter means it becomes closer to the x-axis, steeper and goes away from the x-axis. That's a stretch. And also, if you think about it, if you take the x-axis of a graph and you start to pull it upwards, you start to aggressively start pulling it upwards, you'll notice that the graph actually starts to get a lot steeper. And then when you start to push down on the graph, you start to press down on the x-axis, the graph actually starts to flatten out a lot more. So that's the analogy of a stretch and a compression. And how exactly do we do that? So we know that f of x in this case, y equals mx plus b, y is our x-coordinate. Y equals anything on the right-hand side. So since we're trying to change the y value of the equation, we're going to multiply the entire equation of mx plus b, what y is equal to, by k. We're going to change that whole equation by a factor to then change our y variables by a factor and cause a slant or that stretch or a compression. So a compression or a stretch. So let's take a look at our parent function, 2x plus 2. We're going to change this function by adding our factor of k being equal to 3. So 3, we're going to multiply 3 by the whole equation, 2x plus 2. And this is a property that goes for any value of k that's greater than 1. So when k is greater than 1, it's going to cause a stretch, a vertical stretch. And since 3 is greater than 1, it's going to cause a specific stretch by a factor of 3. Always include by the factor in which you're stretching this by. Now, for any equation, k cannot be less than 1 when it comes to a stretch or a compression. When it's less than 1, it becomes a negative value, and k can never be negative. And then, of course, k can never be negative because of the fact that we haven't gotten to something more complicated, which has to do with reflections. You'll start to get into that in the later terms of Algebra 1. But for now, k will always be positive. But when you add a negative to it, it flips the graph over. But we're not focused on that yet. We're just going to keep k as a positive. And then on the right-hand side, we have that f of x equals 1/2 times 2x plus 2. We're multiplying 2x plus 2 by a factor of 1/2. And in this case, this is a property in which 0 is less than k is less than 1. So whenever k is a fraction, it's actually going to cause the graph to compress. So whenever k is greater than 1, it's a greater value than 1, it's going to cause the graph to stretch. So it's going to come a lot steeper, become a lot more steep. And then, of course, when it comes to a compression, something less than 1 and between 1 and 0, when it's a fraction, it's going to cause it to flatten out and become compressed towards the x-axis. So what exactly would that look like on a graph? So visual translations, what does that look like? So we take our parent function, and then we alter it. We multiply 3 in this case. And if we take a look at our graph, we're going to graph originally our 2x plus 2 function. Now what happens is, we know that when we start to stretch the graph, when we have a value of k that's greater than 1, we stretch the graph. And when we're stretching the graph, we're putting it in terms of the x-axis. This means that when we cause a vertical stretch, it's going to stretch away from the x-axis and come closer to the y-axis. So it's going to draw itself away from the x-axis, trying to go as far away from the x-axis and become closer to the y-axis. So in this case, it's moving away from the x-axis. As you can see, it's moving away, up and down. And now you have your new graph. It's a lot steeper in this case, and it's a lot closer to your y-axis rather than your x-axis. And then on the right-hand side, we have our compression. We're multiplying by 1/2 since it's between 0 and 1. We know it's going to be a compression. And as you can see, our parent graph, 2x plus 2, we're going to start to draw that closer to your x-axis. So now we're moving towards your x-axis on both sides of the graph, and we're moving away from our y-axis. So you're compressing it towards your x-axis. And that's what our new graph looks like. So now, because of your vertical compression, it's going to be a lot flatter. It's going to have a much less of a slope. So your slope is going to be less. And then, of course, with your steeper side, you're multiplying by 3. It's going to be increased with the stretch. And one cool thing to notice here is that whenever you're doing a vertical translation, your x-intercept is always going to stay the same. Your y-intercept is always going to change, but your x-intercept is going to always stay the same. So whenever you're shifting your graph, remember that your x-intercept is your point of rotation, so that x-intercept stays the same, and you're just moving across that like a fulcrum. That's how you change the positioning of your graph. That x-intercept will always stay the same in terms of your vertical stretches and compressions. Now, finally, let's move on to our horizontal stretches and compressions. In this case, we're going to be changing the x-coordinate by a factor. So a horizontal stretch or compression occurs when the graph's x-axis causes the graph to compress towards the y-axis. So this time, if you're going to compress the graph, it's going to start to move towards the y-axis and it becomes steeper, or it can stretch away from the y-axis and become a lot flatter. So the y-intercept will stay the same. Remember, vertical translations, vertical stretches and compressions, your x-intercept stays the same, but in this case, your y-intercept is going to stay the same for horizontal. And how does this look like? How exactly do we, carry out this transformation? So in order to actually stretch or compress the graph horizontally, we're only going to multiply it by the slope and the x value together. So we're going to take k, and we're only going to multiply it by mx. We're going to isolate mx together, not the entire equation. So we're going to take our original parent function. We're going to carry out one transformation. So we'll take 3 as our k value. We'll multiply it by the slope and our x-coordinate, so 3 times 2x, and then we'll leave our y-intercept alone, plus 2. And in this case, we know that 3 is greater than 1. So whenever k is greater than 1, this causes a horizontal compression, because what's happening is your graph is actually becoming more compressed towards the y-axis. It's the same thing as a vertical stretch. That's what a horizontal compression is. It's a very similar concept to horizontal stretch. It's stretching away for a horizontal compression. It stretches away from your x-axis and compresses itself towards the y-axis. And in this case, it's by a factor of 3. Then on the right-hand side, we of course have our factor of 1/2, which is a fraction between 0 and 1, and that's going to cause a horizontal stretch whenever k is between 0 and 1, and it's by a factor of 1/2, so it's going to stretch away from the y-axis and get closer to the x-axis, become flatter. And the only difference between horizontal stretches and compressions and your vertical stretches and compressions is the fact that your point of rotation. So where you're actually rotating your graph to actually change it, that's different. Because for your vertical ones, it's going to be on your x-intercept, because your x-intercept never changes. But in this case, for your horizontal, your x-intercept is the factor that's changing, since your x-coordinate's changing, and you're going to rotate it on your y-intercept instead. That's the only difference. So let me show you that visual translation. We have f of x equals 2x plus 2 as our parent function. We're going to carry out that transformation by multiplying 3 to 2x. Since k is greater than 1, this is going to be a compression, a horizontal compression. So it's going to get closer to the y-axis. But in this case, what's happening here is you're going to be moving across your y-intercept instead, where your graph intercepts the y-axis. Because it's a horizontal, you're going to be moving across your y-intercept. Since x values are all changing, your y-intercept will stay the same, and you use that as your point of rotation. And then on the right-hand side, we have 1/2, which is between 0 and 1. So this is a stretch in this case. It's stretching away from this will be a stretch because it's stretching away from your y-axis. So it's going to be moving towards your x-axis and stretching away from your y-axis. And in this case, it'll become a lot flatter in this case. So it has a lesser slope, unlike the horizontal compression, which has a greater slope. So it's hugging closer towards the x-axis, moving away from the y-axis. And as you can see here, it's rotating along its y-intercept. The y-intercept is the only point that actually stays the same for horizontal transformations, stretches and compressions. And then for the vertical stretches and compressions, your x-intercept is the point that stays the same. It's the only point that stays the same, and it's the point that you're rotating across. All right, everyone, so that'll be it for today's video. I know this was a lot, but this is a very important video, and this is like something that you build up on as your core in Algebra 1, throughout Algebra 1, and throughout your math career as high schoolers and middle schoolers. So this has been the eCoreAcademy e-learning platform. Please make sure to like and subscribe if you like this video. Utilize that comment section down below and reach out to us using our email at eCoreAcademy@gmail.com for any questions or concerns. Also, check out our website at www.ecoreacademy.org. We have full unlocked access to quizzes, note sheets, worksheets, anything you can ask for. All of that's free to access there. Literally full online access to what we offer. Everything that you can possibly need for an in-school course, it's there for you and to help you get through each and every single one of our courses. Also, check out all of our social media accounts: Facebook, Twitter, Instagram, Pinterest, and TikTok. See what kind of interesting new content we also have out there apart from our YouTube channel. We post a lot of funny stuff out there and interesting topics. So check that out just as a brief distraction from your day, and use those platforms to actually share all of our posts. Once again, everyone, I hope you guys enjoyed this video. This has been AJ, and I'll see you guys in the next one. Peace!